Hello everybody and welcome to our next session on algorithm design. We are discussing the divide and conquer method, and this is the second lecture on the divide and conquer method. In our algorithm approach of these 6 steps on the right side, where we have the initial solution as a recursive definition, then we explored the possibilities. Here is where we are now currently working on, is where we are going to make a choice. And among the ways in which we make a choice, how do we balance the split is what is called in our parlance the divide and conquer method of algorithm design. However, they are all very intricately connected with data structuring and complexity analysis. And today we shall go through the series of sorting problems to really understand the whole process of divide and conquer. So, in terms of our recursive definition and the basics of divide and conquer, we had our function f of x, and this f of x had a base condition, as we saw, b of x, and once we had the base condition, as soon as the base condition was evaluated, we returned some j of x. Then we had our recursive part. The recursive part had 3 steps. The first is the decomposition function, d of x, and this decomposition function created some subcomponents. Once we took d, we got this x broken up into subcomponents. Then we had the actual recursive call. And through the recursive call, we got back y, which is y1, y2 to yp is equal to f of x1, x2 up to xk. And after we have got this recursive call and we have got back the results of the recursion, we have our recomposition or our recomposition function r, which takes the values of y and composes the values of y and produces the result. That means as soon as these k solutions, this is k, these k solutions are returned, then the solutions to these k's are then recomposed into some z1, z2 up to zp is equal to a recomposition of y1, y2 up to yk. So, as soon as we now recompose the function, and based on this recomposition, we then return z, which is the result of our recomposition function. So, whereas these are the steps, and based on these steps, our main approach here in the divide and conquer method is to concentrate on how do we do the decomposition, how do we do the recomposition. So, these are our basic steps. So, our concentration is on the decomposition and recomposition. and these decomposition and recomposition have costs involved, and based on these costs involved we get the recurrence relation for the time complexity and also we get the recurrence tree or recursion tree where nodes have costs corresponding to D and R, and obviously there is a cost of the base condition. We also have properties of the functions, properties of D and R in terms of their associativity, commutativity, etc., etc., which enables us to see how we will evaluate. So, other than the decomposition and recomposition functions, the other important part is the recursion structure. From which we create our required insights on how the problem is solved by D and C, and D and C means divide and conquer, and try to optimize our choices in the divide and conquer approach, both in D and R. What are our choices? As we have seen, we provide generalized decomposition rules which provides multiple options, and based on those options we can choose which option optimizes our time complexity best. And based on the recursion structure we also choose our data structures. So these choices and our data structure choices yield our final algorithm that we will get. We have been discussing sorting and searching problems, and in the general case the searching problem is search LS, where L is a set or list of elements from which we try to find out to search our required element. And what do we search from? S is the set of elements which we try to find in L. L and S may be ordered or unordered, and depending on whether L is ordered or S is ordered or L and S are both ordered, the algorithmic strategies differ, and we have discussed this in great details in our previous lecture. And from there we came up when L is ordered and S is a single element, then we came up with the notion that the binary search algorithm is the best divide and conquer choice. On the other hand, we also noticed the recursion tree in ordered L based search gives a binary search tree or BST structure. For example, if we had a set of elements, say 7, 8, 12, 15, 18, then this yields a structure. Suppose our first choice is 12, then on this side we have all the elements less than 12. On the right side we have all the elements greater than 12, and again recursively this would be, let us say, 8, and then this side would be 7, this side would be null, that is, there is nothing on this side. So this is, let us say, we define null as a null pointer like this. This side maybe we could have 15, and then only there would be an element 18 on the left side, and this side would not have anything. So let us, for the time being, remove. So this is how it is. So this is a binary tree, and in this binary tree these are all grounded, and these are all grounded. This is how the recursion looks like, and later on we will see that this structure itself is very optimal for our various kinds of sorting and searching problems, and this will be one of the most popular data structures that we will be using throughout. We also mentioned that we would like to have a height balanced binary search tree, which is the recursion structure, a height balanced binary search tree that minimizes the length of the longest path is optimal in the worst case. So this data structure, which comes up from the recursion tree of a search problem, especially when the list L is ordered, is a very important data structure for us to remember. There are several variations of this. Another alternative data structure that we discussed when we discussed the max finding, the max and the second max problem, is also the heap data structure. So there is the other data structure which is also called the heap data structure, and we shall discuss this heap data structure again sometime when we discuss our method. So there is also another data structure which is called the heap, which can also be used for such recursion trees definitions. but we shall discuss in more details to see how this binary data structure, which in a sorted element enables us to do several things that we would like to do. Now we move on to the sorting problems. And in order to solve the sorting problems, we notice that there are several ways in which we can define the decomposition and recomposition function. So let us look at the first sorting problem, the sorting by removal of the maximum element. So our first definition, we will see about 4-5 kinds of definitions of sorting problems, and the first problem that we will do is sorting by max removal. So our sort 1 L, what does it do? If L is equal to 1, return, so if L is less than equal to 1, return L. So either it is 1 or null, it returns L. Otherwise, let X is equal to we call a function max L. So we get the maximum element of L and let that be X. Then we find L1 equal to L minus X. We remove X. So this is remove X from L. So this is the max removal method. Then we again call sort 1 on L1 and we get M1, which is the sorted value of L1. And finally we create M is equal to X concatenated by, here this is a concatenation operator, M1, which means, so this is a concatenation operator. The concatenation operator puts X in front of M1 and creates this list, and once we have M, we return M. It is not difficult for us to see how this occurs, and the whole recursion structure, suppose we have an initial set 7, 1, 8, 2, 3. Then this algorithm would first remove the maximum element here. So 8 would be removed and it would call it recursively on 7, 1, 2, 3. Then 7 would be removed. It would call it on 1, 2, 3. Then 3 would be removed. We would call it on 2, 3. Then 2, 1. Then 2 would be removed. We would have 1. And then at this point in time, the recompositions will start occurring. And how will the recompositions occur? Here this will form 2, 1. This will recompose here to form 3, 2, 1. This will recompose to form 7, 3, 2, 1. And finally this and this will recompose to form my final solution 8, 7, 3, 2, 1. You will notice that this concatenation operator, so our decomposition operator, what is our decomposition operator here? Our decomposition operator is this part. This is our decomposition operator, D. This is our recomposition operator, R. And this is our recursive call in between. And as you can see, that our normal mechanism of the decomposition operator, to find the maximum of n elements takes order n time. Therefore, the time complexity of this if I will have to call it on Tn minus 1, and I will require order n time to find the maximum. And if we do this, then we can see that this algorithm, in the brute force, this algorithm will become order n squared. So this would be an order n squared algorithm. Now, this is one approach where we have defined our decomposition and recomposition functions. Our decomposition function is order 1 time because it is just putting it in front of the resultant list, but our decomposition operator is order n time. Now let us see whether we can improve this order n squared algorithm or not. So we come back to our understanding and analysis of the data structure. This we had done when we solved the max 1, max 2 problem. We noticed that we can form a data structure during the first max, and this data structure we had called tournament, but as we shall see later on, a more efficient version of that data structure is called a heap. And in a heap we stored this based on a knockout comparison. So during the first max we do it differently, and then onwards finding the rest of the max values makes it much easier, is done on the heap data structure, is done on the heap or tournament data structure. Let us come back and see how that occurs for our example which we have given here. So our example is 7, 1, 8, 2, 3. What we decided was that we will create this data structure which will do a comparison not one at a time, but in a pairwise manner, and create this comparison tree. This is when we do the first max, and based on the first max we will create this comparison tree of the largest numbers, and get the largest number out in place here, and we will create this as the first data structure, and then the next max onwards for the next max onwards we will, so first max will create this heap data structure, and the next man onward will manipulate this heap. And how does it manipulate the heap? As we had said, we will mark this we will go along the base path and mark this as null, and we will update these values here. This will become 2, this will become 3, and this will become 7, and so on and so forth. Once we do this, then we know that our complexity changes. The first max is computed in order n time, and all the rest of the maxes are computed in order log n time. Therefore, our algorithm then becomes, based on this computation, the algorithm now will become order of n log n plus n, which is the same as order of n log n. So now we have seen that while this was our basic algorithm, while analyzing this recursion structure, where our main part was the decomposition function, and this decomposition function we had already written in a recursive manner. Now, looking at that recursive manner of how we wrote the decomposition function, we saw that we could write that recursive definition for max in a different way, and we therefore use the max finding and break up the max finding into two parts. And once we have broken up the max finding into two parts, we then define this sorting problem and create two parts to the sorting problem. So we now rewrite and finalize the algorithm. So our sort 1 new L, it obviously we know that if L is less than equal to 1, return L. Otherwise, we do two things. We get x1 is equal to max 1 plus heap creation data structure of L. So this is the first time, so this is the first max. Once we have done this, then we now call this whole thing on iteratively on this data structure, which this data structure creates the heap H. Once we know that we have created this heap H, now we can finalize our algorithm for I equal to 2 to size of L do. We now will do xi is equal to get max from H, because we have created this heap data structure. So we have removed the max here, or we could also, instead of removing the max, we could here, which creates the heap, and we could even start from the beginning instead of removing the max. Let us say what we actually do is we don't do anything, we just create this heap data structure in the first instance. So this just returns our heap data structure. This returns our heap data structure, and then from I equal to 1 to n, we just do get max hi, and all we now do is concatenate. So then, and we initialize our sorted list L, the final that we want to do, M equal to null. We get this max, we write xi is equal to M, and we put it like this. Sorry, this is not xi. We rewrite M. So what we do is M is equal to M in front and xi is put after this. And once we get max from M, we also remove. So this get max, instead of calling it get max, we call it remove max. Instead of get max, since we have to remove this, get remove max. So we will remove the maximum element from this list. We remove max from H and call it Hi. We add Hi, Xi at the end. That means here what we are doing is we are performing a NQ operator. An NQ operator into M. We have created M as a Q, and once we do this, then we will simply get our final algorithm. Let me also make a small change here. This so this is how we get our final algorithm, and we know that in order to do this algorithm, we have performed our algorithm in this way, and therefore we have created the heap, and for this heap, by doing this, we finally get an order n log n algorithm for sorting using the sort max. So this is the step in which we have done it. Just to repeat, we looked at D and R. Here there was no other choice, but here in this case the max operation itself had a choice. There were various ways in which we could do max, and we have seen that before in our previous method, and we use one of those choices of doing max, wherein we build this data structure. The max could have been done in hundreds of ways, but we build this data structure, and after we build this data structure called a heap, we then see that we can convert this part whole into an iteration from 1 to n, but using that data structure as a heap. So once we convert it from 1 to n, we now get the max one and create this heap data structure. Then from the beginning we start removing one by one the maximum, put it into a queue, and as we put it into a queue, that queue develops into my final algorithm. So starting from an algorithm which had a basics of order n squared complexity, we started looking at the choice points of the max of the decomposition operator, and based on the detailed choice points of the decomposition operator, we were now able to get an order n log n algorithm. We now move to a new definition. A new definition which is a different way in which we can do our sorting. So now we define a new sorting algorithm called sort to L. Here let L equal to x1, x2 up to xn. Again our base condition, obviously, if L is less than equal to 1, return L. Now here in the previous one where our decomposition operator was removing the max, here we remove any element. In fact, we remove any element from, so choose xi from L, and then let L1 is equal to L minus xi. Let M1 is equal to the recursive sorting of L1, and then we write M is equal to insert in L1, insert xi in L1 to get M, which means insert, since L1, sorry, this will not insert in L1, it will insert in M1. This will insert in M1. That means we have got our sorted array, L1 is sorted and is returned as M1, and so inserts xi in its proper place in M1, which is the sorted version of L1, so that M is sorted. And once we do this, we will return M. Now, if we analyze this more carefully, we see that this is our base condition. This is our decomposition function. This is our recursive function, and this is our recomposition function. And how do we insert this element xi in a sorted list mi? We know that if we have to insert that element, then we have got several choices. The first choice is we can store xi. So now this whole thing, the complexity will be, we know that this complexity of choosing any element is order 1, and here we have an option of which one to choose. Now this choice that we had made earlier in our previous case was the choice of max. Here we have found if we choose max, then the insert operator is a simple concatenation operator. That option we have seen. Now we can choose any other element which is an order 1 complexity, because if we tried to choose max, we had an order n complexity. We now want to choose one which is order 1 complexity. But as soon as we do that, we see that a brute force mechanism of doing this will give us an order n complexity of insertion. So there are, this question, what is the complexity here, is an important question. Now that we have decided to do the decomposition in order 1 time, that means we randomly choose an element, or we choose the first element, or we choose the last element, then we have to do this insertion. Now in order to do this insertion, if we analyze very carefully, our recurrence relation now becomes Tn is equal to Tn minus 1 plus order 1 for decomposition, and the function here is the cost of the recomposition. Now if it is a linear insertion, then this will become order n. And if it is order n, then in this case the algorithm will become order n squared. But we can say that since M1 is sorted, why don't we use binary search? That means, suppose M1 is an array. Then we can do this, then we can do the insertion in order log n time. At least we know order log n time find operation is there, because we have just done it, that we can use binary search to find an element, at least to find the position of an element. If it does not exist, binary search will find the position. But the problem, but in an array, the insertion is an issue. So that is where we come to the data structure. So based on this, we come to the required data structure, saying that how are we going to store the elements of M1 so that insertion can be done in order log n time. That is where we will need what is called the binary search tree data structure. That means we will use the binary search tree data structure for M1. And therefore, the algorithm, instead of returning an array or a list, will now return a binary search tree. So how does it happen? As we had seen earlier when we discussed binary search trees, here, and we had also discussed binary search trees when we discussed searching, we said that effectively the recursion structure forms what is called a binary search tree. So if we come to what we are trying to do here, what we will see is the following. Suppose my initial L was 7, 1, 8, 3, 2, and suppose we have removed 7 as our first element, and we recursively call it on 1, 8, 3, 2. When it returns, then this returns the binary search tree data structure. What is the binary search tree data structure that it returns? The binary search tree data structure that it returns is, it is 3, 8, 2. I'm sorry, our binary search tree data structure, the format has to be made clear. How did we make the format? The greater one is on the right and the smaller one is on the left. So so if this is 3, then this side will be 2 and this side will be 1, this side will be null, this side will be 8, and 8 will have no child here and no child here. So this is what is returned. Now I have to insert. Now my job is to insert this 7 inside here. So now how will I insert in this binary search tree? I will check with 3 with 7. Once I check 3 with 7, I will check whether it is equal to or not. If it is equal, then I will just increment the count by saying that there is a duplicate element. Otherwise, if it is less, I will recursively move to the left. If it is right, I will recursively move to the right. So here I will move 7 here. So I check 7. I move 7 here. Then I move 7 here. And I create this node and add 7. And once I do this, then this binary search tree is returned as the outcome of this. This now returns. And we see that if we do this data structure, then by doing this data structure, we will now be able to actually create a binary search tree in return. And once we have a binary search tree, then we will be able to find out the elements in any sorting order by a traversal of that binary search tree. So finally, the algorithm will return a traversal of the binary search tree will provide us with the sorted list. And this traversal only once at the end will require order enter. Based on this, the complexity of the algorithm now becomes Tn there are n steps of insertion. The removal, as we know, the decomposition operator is order 1 complexity. Only the recomposition operator. So the algorithm will now become Tn is equal to Tn minus 1 plus order n. And this will lead to order n log n complexity. And we can add this final term here, but it will not add anything else to this order n log n complexity. So based on this whole thing, our final algorithm for this sorting will then become sort M2 final L. And I leave it to you to determine how. So number 1, we will have to define a binary search tree data structure. Which will be returned from this final algorithm. And this binary search tree data structure, as you can see, the operations on this binary search tree data structure will be insert, and this operation can be written in a recursive fashion, and I leave it to you to write. So this binary search tree will have an insert operator. The other binary search tree will be having its traversal operator. And there are 3 kinds of traversal in a binary search tree. One is called the pre-order traversal, the in-order traversal, and the post-order traversal. And depending on whether in this in-order traversal you do a left or a right first. So in this order traversal can also be done left to right or right to left. So this traversal can be done left to right or right to left. And based on this, and this traversal can also be written. So this is another recursive routine. And once we do this traversal, we will be able to get our algorithm completed. The most important thing of this binary tree data structure, it has to be a balanced binary search tree. That means we cannot have the binary search tree in such a way that if 8 was the root, then 3 was the child, then all of them, for example, a binary search tree which is like this: 8, 7, 3, 2, 1, and these are all having nothing. This is a skewed or unbalanced BST. A balanced BST is one whose height of the longest path is minimum, and a balanced BST has got height of order of log n where there are n elements. And these traversal algorithms, for example, a traversal would mean if we want to print the elements in a particular order, say we want to print the elements in descending order, then what we would do is we would do what is called an right to left in order traversal. So we would first recursively call the algorithm on the node on the right, then we will print the node in the center, and then we will recursively call the element on the left. And if we do that for a leaf node, we will print that node. And if we do that in this sequence, if we do that for a sequence like this, so suppose we have got 3, 2, 1, 8, 7. If we have this one is a balanced tree. This one is a balanced tree because there are 5 elements and the log of 5 taking the ceiling yields 3. So the in-order traversal of this, would first, right to left would go here, since there is nothing here. This is the first node that will be printed. Then, because the algorithm of in-order traversal is R child in order right to left, R child, so we call it on in order R child. Let us rewrite this carefully. In order L, which we give it at the root of the node. So in order traversal at a node. So the first thing that we do is we call it on, and we are doing a right to left in order traversal. So we are doing right to left in order traversal. So we again call it at if node not equal to null. If node is not equal to null, then we do the following. We do a right to left in order of the right of the node. Then we print the node. and then we do a right to left in order of the left child. So this is how we do. So here we would, from 3 we would go to 8. 8 here is null, so this returns from here. This is the first node that would be printed, or this is the first node which would be put into the queue. Then it would go to the left of this, both the children of 7. So this is the second node that would be printed. Then it would come here. This is the third node that is printed, because in order between calling the right child and the left child you are printing or choosing the node. Then you will come here, because the right child is null. This is the fourth node in the sequence. Then you come here, and this is the fifth node in the sequence. So by doing this, you will enlist the nodes 8, 7, 3, 2, 1, and you will get this in the sorting order. If you wanted to do it in the reverse order, then you would have to do left node first, left child first, then the node, and then the right child. So this sort of traversal techniques can also be written in a recursive fashion. So by doing this, we now have an order n log n algorithm for sorting in a different way. Here, in the previous one, where we chose max as the decomposition, we had a different decomposition function. The choice of x1 was not order 1, it had a different complexity, whereas in that one the recomposition was an order 1 complexity, and now we are able to combine both of these together. Based on this, we shall now move on to the next sorting algorithm, which is another set of 2 more sorting algorithms, which are very important algorithms, which again looks at the decomposition and the recomposition functions,